Hello everyone. Today's learning objective is about Pearson Theory, HSAB concept. So, HSAB concept it is an initialization for hard and soft acid bases, always known as Pearson acid base concept. HSAB is widely used in chemistry for explaining stability of the compounds, reaction mechanism, pathways. It assigns the terms hard or soft and acid or base to chemical species. So, according to this theory, Pearson, according to HSAB principle, hard acid prefers to form bond with hard bases and soft acid prefers to form bond with soft bases. To predict the stability of complex or coordinate compound formed between acids, that is metal ion, and bases ligands, Pearson has suggested this rule. This rule is Pearson's HSAB principle. Hard, soft, acid bases. HSAB theory. So it is a qualitative concept introduced by Rolf Pearson to explain stability of metal complexes and mechanism of the reactions. So the types here hard Lewis acids. So in 1960 Rolf Pearson developed type A, type B, classified Lewis acids and Lewis bases as hard, borderline, or soft. Hard and soft acid bases, HSAB principle, it is the qualitative concept which was introduced for the acids and bases. So, according to this concept, hard acid prefers binding to the hard bases to give ionic complexes, whereas soft acid prefers to bind soft bases to give covalent complexes. This is referred as the hard soft interaction principle. Hard soft interaction principle, HSIP. Now, the types are hard Lewis acids. These are characterized by small ionic radii, high positive charge, strongly solvated, and these compounds have empty orbitals in valence shell. And these have high energy, lower unoccupied molecular orbitals. These are called as the hard Lewis acids. But these are characterized by the small ionic radii. So, and they have high positive charge and empty orbitals in the valence shell with high energy, lowest unoccupied molecular orbitals. The second type is Lewis acids. The second type is Lewis acids are characterized by soft. Lewis acids are characterized by small ionic radii, high positive charge, strongly solvated, empty orbitals in valence shell, high energy lumos. Both of them are the Lewis acids. Okay, and here, both of them almost here. This it's a wrongly typed. This greater ionic radii and less positive charge and less solvated and filled orbitals in the valence shells with low energy molecular orbitals. Now coming to the hard Lewis bases. These are characterized by small Here, I've told you hard Lewis acids. Quite opposite to this is soft Lewis acids. Here, the typing mistake has been here. Small ionic radii for hard Lewis acids. And here, larger ionic radii for the soft Lewis acids. High positive charge, low positive charge. Strongly solvated, less strongly solvated. And these are having empty orbitals, it is having the filled orbitals. Highest energy LUMOS and here low energy LUMOS. Now coming to the hard Lewis bases, these are characterized by small ionic radii, strongly solvated, highly electronegative, weakly polarizable, and with high energy HOMOS. Okay, so quite opposite. Now coming to the soft Lewis spaces, these have large size, intermediate electronegativity, highly polarizable with low energy HOMOS. And coming to the borderline Lewis acids and bases are intermediate properties. These have the intermediate properties. The borderline acids or bases, both of them have in between properties to that of hard and soft. So hard and soft bases, acid bases are small, non-polarizable, whereas soft acids and bases are large and more polarizable. The stability of the complex depends on the type of the ligand and metal ion. The stability of the complexes or the coordination compounds depend on the type of the ligand and metal ion. For the formation of the stable complex, the type of metal ion ligand must be known. So, Arna, Erland and Chart and Davis have divided metal ions into different types. Of course, two types or classes. How is the polarizability? We'll see. The capacity of a group of atoms in a molecule or an ion to polarize its electron is polarizability. Capacity of a group of atom in a molecule or an ion to polarize its electron is polarizability. Example, you take ammonia. There. On polarization, what's happening is you can just notice what's happening is just nitrogen is getting partial negative charge and hydrogen is getting partial positive charge. So, depending on this, the chemical species are hard and soft. So, less easily polarized species are hard. Electronic electrostatic interactions it have, that is hard. And if it is more easily polarized species, then that is soft chemical species. And electron sharing or covalent interaction is present. If that covalent interaction is there, then that is soft. If ionic interaction, then that compound is hard, that chemical species is hard. Now, what is the principle? The Pearson theory and the principle. According to HSAB, hard acids prefer binding to the hard bases and ionic complexes are formed, whereas soft acids prefer to bind to soft bases. They prefer to bind to the soft bases. Now, to give the covalent complexes. It is sometimes referred to as hard soft interaction principle, HSIP. As I've told you, it is HSIP. So, according to this concept, Pearson's concept, hard acid prefers binding to the hard base and ionic complexes are formed. Soft acid prefers to form soft bases to give covalent compounds. So, this is HSIP principle. The large electronegativities differences between hard acids and hard bases give strong ionic interactions. Give strong ionic interactions. The electronegativities of the soft acid and soft bases are almost the same, hence they have less ionic interactions. So the electronegativity of the soft acids and soft bases are almost the same. Therefore, they have less ionic interactions. The interactions between them are covalent. So if the both interaction is soft, then that is a covalent interaction. And if the interaction between hard acid and soft base and soft acid and hard base are most popularly polar covalent and they tend to be more reactive, less stable. If such interaction is there, they are found to be more reactive and less stable. So, covalent compounds readily form either more ionic or more covalent compounds. They form either more ionic or more covalent compounds if they are allowed to react. Now I'm going to tell the characteristics of here. They have categorized into different classes. Type A or class A metal ions, that is acids. Alkali metals, alkaline earth metals, lighter first transition metal ions in the higher oxidation state, boron, aluminium, silicon ions, and lighter metal ions without d electrons. These are found to have lesser number of d electrons called type A or class A metal ions. These have small size, high polarizing power, high oxidation state. They combine with the small size, less polarizing ligands. Their outer electrons are not easily destroyed. They form stable, yeah, I'm telling about the acids. They form about the stable complexes with ligands in which donor atom is first element each group in the periodic table. So these are the type A type of metal ions, that is acids. In the periodic table you can notice here all these D block elements are hard acids. The beryllium, these all compounds. And to the bottom, these are the soft. The upper ones are the hard. Here. The violet line, you can see the border line. And these are the soft acids. And coming to the bases, you can see all these form the bases. These all form the acids. And these are all the border lines. Okay. The blue ones, acids, and these are bases, and these are the borderline. As I have told you, according to HSAB concept, hard acids prefer binding to the hard bases to give ionic complexes. Soft acids prefer binding to the soft bases to give covalent complexes. This sometimes it is referred as hard soft interaction principle. You can see here HSAB principle. Hard prefers with hard base. Soft acid never prefers. Hard acid prefers with hard base. And soft acid prefers with soft base. But here, this soft acid and hard base is not preferred. Soft base and hard acid is not preferred. Okay, so this is the preference and this is the principle. As I've told you, type A class metal ions characters were discussed. Now type B metal ions, Lewis acids, that is soft acids. The characteristics are heavier transition metal ions is having lower oxidation state. Metal ion with lower valency or zero valence metal ions in the metal carbonyls come under this category. They have large size, low positive nature, zero oxidation state, highly polarizable. Their outer electrons are easily distorted. These combine with a large size and highly polarizable ligands. These form stable complexes with ligands where the donor atom is the second element of the each group in periodic table. So type A, type B ligands are classified into two types. So previously metal ions are classified into two types. Type A metal ions or class A metal ions. Type B metal ions or class B metal ions. So type A are the hard acids. Type B are the soft acids. Now coming to the ligands. So about the acids we have discussed, I'm going to explain you about the ligands. So the key characters here. Key characters. Before explaining key characters, how are the ligands? Type A ligands, type B ligands. Type A or class A ligands. Ligands containing donor atoms of higher electronegativity are class A ligands. Ligands containing donor atoms of higher electronegativity are class A ligands. Fluoride ion, water, NH3, NR3, etc. These have low polarizability and great tendency to coordinate with type A metal ions. The decreasing tendency of some ligands form complexes with type A metal ions. See, type A or class A ligands are fluoride, chloride, bromide, iodide, oxygen, sulfur. You can see all the seventh group, sixth group, fifth group elements. Oxygen, sulfur, selenium, tellurium, nitrogen, phosphorus, arsenic, antimony. All these are the class A or type A ligands. Coming to the type B or class B ligands. Ligands containing donor atoms of low electronegativity. Ligands containing donor atoms of low electronegativity are class B ligands. Trialkyl phosphine, dialkyl sulfur. These have high polarizability, greater tendency to coordinate with type B metal ions. Okay, so now let us see the key characters. Let us see the key characters of the type A, type B metal ions, type A, type B ligands. Hard acids, low polarizability, low polarizing power, high positive charge, small size, not easily oxidized. These are not easily oxidized. So the hard acids are hard to get polarized. And hard acids, they have high positive charge. Hard acids have small size. Hard acids are hard to get oxidized. Next, coming to the hard bases. Here low polarizability, even these have the low polarizability. And as hard acids have high positive charge, they spread donor orbital. High electronegativity, you can see. Here high positive charge, here high electronegative charge. And these are small in size. Even these are here. These are small in size. Here these are large in size. These cannot easily be oxidized, and these cannot be easily oxidized. Okay, so now let us see about the soft acids. Coming to the soft acids, high polarizability, low positive charge. Soft acids have high polarizability, low positive charge, large size, easily oxidized. They get easily oxidized. Now coming to the soft bases. Soft bases are highly polarizable. They diffuse donor orbital. Soft bases have low electronegativity, and these are easily oxidized. These are easily oxidized. So hard bases are low in size, whereas soft bases are large in size. Hard bases are low in size. Soft bases are high in size. Okay. These are the key characters for the hard acids, hard bases, soft acids, and soft bases. Now, third category whose characteristics are in between those of hard and soft bases are called as the borderline acid bases. Now let us look on to the type A or class A metal ions and borderline metal ions. Similarly, type B or class B metal ions. So metal ions indicate about the acids. Metal ions are nothing but the acids. Both of them are the acceptors. Now let us discuss the characters taking some examples. Hard acids. Hard acids, d orbitals either vacant or they are not at all existing. Hard acids, if you see, as I've shown you in the periodic table, d orbitals, they are vacant or they don't exist. Now, their size is small and these are not easily polarizable. They are mostly light metal ions associated with high positive oxidation state. These are high metal ions and they are having high positive oxidation state. These are called as the hard acids. Under this category, you have sodium. See in the periodic table, yes, sodium. All these come under the hard acids. Sodium, the first group element, sodium, hydrogen, lithium, sodium, potassium. So the upper part of the first group element. Here, upper part of the first group element. These are all the soft acids. These are the hard acids. See, till calcium and potassium. These are the hard acids. And coming to the bottom one, these are the soft. H plus ion, lithium, sodium, potassium, beryllium, calcium, strontium, manganese, aluminium, gallium, indium, lanthanum, lutetium, chromium, cobalt, iron, arsenic, silicon, titanium. So plus 1 oxidation state, plus 2, plus 3, plus 4. These come under the hard acids. They either have vacant orbital, they are very small in size, they are not polarizable, and these are having good high positive oxidation state. Now coming to the soft acids. Here you are having vacant, quite opposite, here it is full d orbitals. These are small in size. The soft acids are large in size. Hard acids are polarizable, not so easily polarizable. Small size, not polarizable easily. These are easily polarizable. Large in size and easily polarizable. Soft acids. And these metals have high oxidation state. These metal ions have low oxidation state. Okay. And under soft acids, the examples are copper, silver, gold, thallium, mercury, lead, cadmium, platinum, mercury, platinum plus 4 oxidation state, thallium plus 1 and plus 3. So, boron hydride. Still, you have some more examples: uranium, cerium, tin, uranium, vanadium oxide, uranium oxide, molybdenum oxide, boron trifluoride. These are hard acids. Coming to the soft acids, gallium chloride, indium trichloride, carbenes, pi acceptor ligands, iridium, iodine, bromine, oxygen, chlorine, bromine. Here, plus oxidation state. Sometimes I expect the plus oxidation state. Oxygen, chlorine, zero oxidation state. Bromine, iodine, nitrogen, and some of the zero valent metal atoms. Now, coming to the borderline acids. So, borderline have the characters in between the hard acids and soft acids. Now, coming to the borderline acids, iron, these have the characters between these two, hard acid and soft acid. Type A or class A, type B and class B metal ions. In between characters are there for the borderline acids. Fe plus 2, cobalt plus 2, nickel plus 2, copper plus 2, zinc plus 2, lead plus 2, tin plus 2, antimony plus 3, bismuth plus 3, rhodium, sulfur dioxide, nitronium ion, gallium hydride. These have borderline characters between the hard and soft acids. Now let us have a look onto the bases. What are the characteristics for these bases? So hard bases, soft bases. Hard bases, donor atoms are having low polarizability. As we have discussed, these are the donor atoms. Here, these are the acceptors. So, these hard bases, donor atoms are having low polarizability. These have high electronegativity. So, the polarizing power is less, electronegativity is high. These are the and small in size. These are small in size. Okay. These have negative oxidation states. Small in size, negative oxidation state. High electronegativity. Donor atoms having low polarizability, high electronegativity, small in size, negative oxidation state are called as the hard bases or type A or class B ligands. Now coming to the soft bases. These soft bases, the donor atoms are easily polarized. These are large in size. They have negative oxidation state. They have low electronegativity. They have the low electronegativity. Now, coming to the examples. Under hard bases, borderline bases, and soft bases, hard bases examples are water, OH minus, F minus, acetate, phosphate, sulfate, chloride, carbonate, perchlorate, nitrate. Okay, here carbonate, it is CO3 minus 2. The 3 instead of here it has come here, the typing. And similarly, perchlorate here, ClO4 minus. Nitrate, NO3 minus. And this alcohol group, alkoxide, so ether, ammonia, amines, hydrazine. All these come under the hard bases, highly electronegative, low polarizing, less size, and negative oxidation state or zero. Coming to the soft bases, easily polarizable, large size, negative oxidation state, low electronegativity. Examples are dialkyl sulfide, next sulfide, iodide, thiocyanide, thiosulfate, trialkyl phosphine, trialkyl arsenic, cyanide, alkyl cyanide, carbon monoxide, ethylene, benzene, hydride ion. These come under the soft bases. So hard bases are type A or class A ligands. Soft bases are type A or class A ligands. For acids, you call it as the metal ion. For bases, you call it as the ligand. So metal ion is the acceptor, ligand is the donor. Acid is the acceptor, base is the donor. Now, the bases which are having in between characters of hard bases and soft bases are borderline bases. Here, borderline bases aniline, pyridine, azide, nitro group, sulfite, nitrogen, bromide. These are the borderline bases. According to HSAB principle, hard acids form stable complexes with hard bases. Soft acids form stable complexes with soft bases. And coming to conclusion, we have categorized all the compounds, that is acids, bases, the metal ion and ligands. The conclusion is that HSAB theory states that hard electrophile tends to react with hard nucleophile. Soft electrophile tends to react with soft nucleophile. The hard and hard interaction is governed primarily by electrostatic attraction between positively charged electrophiles and negatively charged nucleophiles. The soft-soft interaction is governed primarily by mixing overlap of the orbitals between the LUMO of the electrophile and HOMO of the nucleophile. So LUMO is always the electrophile, HOMO is nucleophile. Okay, so these are the conclusions drawn from Pearson theory. Hard electrophile react with hard nucleophile. Soft electrophile tend to react with soft nucleophile. So electrophile and nucleophile reacts, but hard with the hard and soft with the soft. So hard-hard interaction is governed by electrostatic attraction between positively charged electrophile and negatively charged nucleophile. Soft-soft interaction is governed by primarily by mixing of the LUMO and HOMO of the nucleophiles. We have seen examples of the hard soft electrophiles and nucleophiles and the role played by the HSAB theory in the conjugate addition. So in this conjugate addition, H of A, H of B will react properly. S of A, S of B reacts properly and the stability is maintained. Eh, Also, the HCAB theory is only one of the several factors which determines the outcome of nucleophilic addition to the alpha beta unsaturated carbonyl compounds. So, in the alpha beta unsaturated carbonyl compounds nucleophilic addition, that can be explained basing on this theory. So, here I have to explain you before conclusions, the limitation should be explained. Main limitation of this concept is it is completely general in nature without any quantitative scale of measurement. There is no quantitative scale of measurement. Everything is explained in general. That is the limitation for HSAB principle. Now, HSAB theory considers all chemical reactions as acid base reactions. HSAB considers all the chemical reactions as HS acid base reactions, but these reactions can be better explained when considered in other point of view, not as the acid and base. If other point of view is discussed, this theory can be more, it can be more better. So this principle may not be regarded as exclusive because under approximate conditions only hard acid complex and soft bases may complex, hard acids and hard bases will complex, soft bases and soft bases may complex. Okay, and these can form the stable complexes. So it may not be regarded as exclusive because under appropriate conditions only this combination takes place. Sometimes hard may combine with the soft and soft may combine with the hard. So in such cases, the explanation is not appropriate. So though he has explained, but that is incomplete in nature, and there is no any quantitative scale for measurement. So these are the limitations for the HSAB theory. So he is explaining everything based on the acid-base reactions. He is explaining without any quantitative measurement. And he has taken how the approximate conditions are only taken. Not complete conditions are explained. Only some of the conditions were explained. So here the other point of view is not explained properly. These are the limitations for HSAB concept. So I hope you have understood today's class. So today's class it is the Pearson theory. So Pearson theory. What is a Pearson theory? HSAB theory and the types of the acids and bases and what are the borderlines and what is polarizability, how a molecule is getting polarizable, what is the principle, HSAB principle, Pearson principle, and what are the hard and soft acid bases in the periodic table, and what is the HSAB principle, the key characters for the hard acid, hard base, soft acid, soft bases were explained, and along with the key characters, different examples of hard borderline soft acids are given. Similarly, different examples and the characteristic points for hard bases, borderline bases, and soft bases is explained. And basing on this, conclusion has been drawn for the HSAB theory. Along with this, there are some limitations. So after concluding this, the limitations were also discussed for you. And I hope today's class you have understood my class. And thank you everybody for paying concentration to my lecture.